Okay, good evening everyone. Let's start the class. So today we'll be mainly looking at some problems related to binary search trees. So let's look at the first problem here. So basically for any given binary search tree, you are given what you have to do is find the common ancestors between two nodes, v1 and v2 let's say. And what you're given is instead of the parent pointer, like for each node you're not given the information as in what is the parent of that node, but instead you're given the information regarding the children node, so the left and the right child. Then so there are pointers pointing to those but not to the parent. And you are given you're asked basically what would be the algorithmic complexity if you were to find common ancestors between any two nodes given in the tree. So first just think about it, like think about what actually is a binary search tree and how do we search for any value in a binary search tree. Okay, and then what you have to do is search for two of these values and backtrack it, or in some other way you have to basically find the common ancestor. So just give it a shot. If you guessed it, then you can put your answers in the chat box. Okay, I got a few of guesses for the question. Others also guess quickly. Then we'll see the concept of a binary search tree, what it is exactly. Okay, so first of all, what is a binary search tree? Okay, so let's look at an example. So here you see a search tree. So basically it's a binary tree, which means every node has two children. Okay, and the property of binary search tree is the left child and all its predecessors. Okay, so all the left, so basically you have the root as 8 here and the left child is 3. Okay, and all the children and grandchildren of 3 now will be less than 8. Okay, so you see here numbers 1 3 6 4 7, so these are all less than 8. Okay, and the right child of 8, the root 8 is 10. Okay, and the right child and all its children and grandchildren, so 10 14 13 here, so they'll all be bigger than 8. Okay, and this property is true for every node in the tree. So all the left children and grandchildren will be less than the node, and all the right children and grandchildren will be more than the node. Okay, so the first question you require to solve this is, if I give you this binary tree, okay, and I ask you to find the position of, let's say, the node 7, okay, here, which is given here, and you have to basically look at the tree and to search for any of the values in a tree with n nodes. What do you think will be the time complexity of it? So that is the first question that you have to solve in order to get the whole question. So just the first question is, if you're given any binary tree with n nodes and you want to find a particular value in that tree, so you may either want to find if that value is even there or not in the tree, and if it is there, then at what level or what node number it is. So what do you think would be the time complexity of finding just one value in a binary search tree? So you can give it in
Logging.
okay, and why will it
Logging.
be log n? How will it be log n?
Suppose
Yeah.
after every iteration, we have the search space.
Okay.
So if we have to go down, say, from 32, then 32 to 16 to 8. So our number
Yeah.
of elements, the search space reduces to half.
Yeah.
And then we take a log. It's basically binary search.
Yeah.
So we just have to go left or right uh, as per, if the value is less, then we have to go left, and if the
Yeah.
value is greater, then we
Yeah.
have to go right. So
Yeah. That is correct. So thank you, Rahul, for that. And that is exactly correct. So if we have to find 7 here, let's say in this binary tree, then you start at the root node. So we'll always start at the root, and 8 is given here, right? Now 7 is less than 8, so we are going to look at its left children and grandchildren. So we are left with this tree 3 1 6 4 7. Now we'll look at the next, just the next child, so left child, which is 3. Now 7 is more than 3, so we are going to look at right children of this third node, so which will bring us to 6 4 and 7. So now with in relation to 6, 7 is greater, so it can only be the right child of 6 or in the grandchildren of 6. So we come at 7 and we stop our search. So essentially at each level we have to either go towards left or right. So this is the only decision we have to make. Are we going to go towards left or right? And at each level we are just checking or comparing the value of 7 with only one node in that level. And if the total number of basically nodes are n in a binary search tree, then, and if it is like a complete binary search tree, like all the nodes are filled, then it will have log n levels. So the order of the search would be log n. So you are just looking at every level, and at every level you are only looking at one particular node, and they are log n level, so the search complexity is log n. Let me know if this is not clear to you, or if you have any doubts in this, like how search complexity is log n, order log n in a binary search tree. Okay, so let's say you want to find one particular value in a binary search tree, and you want to know exactly what node is corresponds to that particular value. So in the example that is given, we are going to try to find 7, or let's say we'll change the example now, and we want to find 13, okay, in this binary tree. So we start at the root node, which is 8, okay, and the value we have to search for is 13. Now 13 is greater than 8, so we know that 13, if it is there in the tree, it can only be in right part of the tree. So right children and grandchildren of the root node 8, which brings us to 10, basically the right child of 8. Now when we compare to 10, we know that 13 is greater than 10, so again we have to look at the right child of 10. Okay, so we come to 14. Now we know that 13 is basically less than 14, so we have to look at the left child of 14, and we come to 13, and we have found the element that we started to look for, and we stop the search. So at each level, if you'll see, like when we were at 8, we just compared a value, then went to 10, and then compared a value, went to 14, and then to 13. So at each level, maximum nodes that we'll have to check for and compare the value against 13 is just 1. Okay, and if there are n total number of nodes, so you will have log n or order log n levels. Okay, so at each level you are comparing just one node, and there are log n levels, so your search algorithm would finish in order log n. Is that clear? Okay. Okay, so given this information, I want you to try this question again. So now you know how much time or what must be the algorithmic complexity of finding either V1 or V2. Okay, and now what you have to do is find a common ancestors of V1 and V2, and think about how much time complexity will that algorithm have if you're looking for a common ancestor.
Can I speak?
Yeah, sure.
But I haven't found the answer yet because I'm a bit confused about the process. लेकिन मैं एक बार अपना सर्च मतलब thought process शेयर कर देता हूँ. Hello?
Yeah, go ahead. Yeah.
Am I audible?
Yeah, Rahul, you're audible. Go ahead, what you were saying.
Okay. Thank you. So, first of all, it is a balanced search tree. So it means that every tree has a left and right. In every subtree has a left and right child.
Okay.
Now we are given two nodes. Secondly, in the linked list or whatever data structure we use, or rather node, we don't have the parent pointer. That is an important information. So what we cannot go up. We cannot go up.
Yeah.
So one way or the other, we have to go down one way or the other.
Yeah, true.
Now when I think about the worst case, अगर हम लोग एक बिल्कुल simple case लें कि it's in the balanced BST balanced search tree, the V1 and V2 are basically first and last element of the sorted array of that the sorted array which the BST stands for basically.
Yeah.
So if it is first and last element, then the case is trivial because we already know कि जो root node है वही हमारा ये होगा least common ancestor होगा.
Okay.
बस यहाँ तक ही मैं पहुँच जाऊँ तक.
No, but your thought process is correct actually. That you have to start from the root node and you have to come down to search for each of this V1 and V2. And how your search is progressing, depending on that, you will know the common ancestor. And the worst case of this search will be log n, but it won't be the average case or anything. It will be the worst case that you have to look at all the levels to find the common ancestor. Okay, so I'll just give you another minute to try the question, everyone, and then we'll look at the answer. And if you have guessed it, then you can put the answers, like just the option number you can put, like
वहां
A, B,
जाते
C,
ही
D.
बिल्कुल वीक हो जाता है कनेक्शन, और मुझे बस, मैं 10 मिनट में घुस वापस आके आता हूँ, फिर फोन दे दूंगा आपको। वहां पे कनेक्शन ही नहीं है।
Okay, let's look at the solution. So if you're given to find, basically let's say in this tree itself, we want to find the common ancestor of 4 and 13. Okay, let's say. So what are we going to do? So first we are going to look for 4 itself. We start at the root node 8. Okay, we know value of 4 is less than 8, so we move to the left child 3. Okay, now 4 is greater than 3, we move to the right child 6. Okay, and now 4 is less than 6, so we go to the left side and we find 4. Now we have a trace, okay, of the nodes that we have visited in the search. What is the trace? 8, then 3, then 6 and 4. Okay, and similarly if we look at 13, then we'll get the trace as 8, 10, 14 and 13. Okay, so now step by step as you're doing this search, so you start with 8, okay, and in both values the next is 3 and 10. Okay, so at the next value itself the search has gone in different direction. So it started with a common root 8, and then for finding 4 we went to 3, and for finding 13 we went to 10, basically to the left or the right part of the tree. So basically whenever you're searching for these two values, the first node, okay, where the difference starts, okay, so the node just prior to that is the common ancestor, which is 8 here. So if we would have done it the same exercise for let's say 6 and 1, okay, so will the trace that will have is 8, 3 and 1 and 8, 3 and 6. Okay, so the search diverges at this node 3, okay, because after that one search goes to the node 1 and the other search goes to the node 6. So this is a common ancestor, the least common ancestor, this value 3. Okay, so all in all you're doing the same process as you were doing before, looking for value v1 in the tree and looking for value v2 in the tree. Okay, and what you have to basically figure out is the first node which is different in the search path. The node prior to this, like, or the last common node will be your least common ancestor. Okay, I hope this point is clear. Now because both of these searches will take log n and log n value, like as Ram put 2 times log n, but we are looking at the order of the search, so 2 times log n is basically order log n, so your answer will still be log of n. Okay, searching for one of the values take log n, searching for another value take log n, and we just need to mark the node where the first path diverges, and that is your common ancestor, and which will be log n order. Okay, in case you guys have any doubt about the question or the solution, anything, so you should ask me right now. Okay, I hope this example, this problem was clear. And this is the worst time complexity. Okay, like just keep that in mind. So let's say here we were looking for common ancestor of 1 and 6. Okay, so here we just have to go 2 levels, like we do not need to go to all the levels of the tree. So log n is your worst time complexity. It might take you less than time to find the common ancestor, especially if you're not looking at the leaf nodes. Like if the nodes are like up in the tree or near the root, then you'll only have to search for a couple of levels before you find the common ancestor. So the log n is the worst time complexity, worst case complexity of this algorithm. Okay, keep that in mind. Okay, with that we'll move on to the second problem. So here you are basically given a method to traverse the tree, and what does tree traversing means? How we were looking for a value in the binary search tree, we start at the root and then we either go left or right. Okay, in traversing the tree, it's kind of like that, but you're visiting all the nodes of the tree and you're doing it in one particular order. So here the method of traversal that you're given is basically you first visit the left node and then you visit the right node and then you print the value of that node itself. Okay, and just given this traversal method, you're asked about some statements, and just read them out and see which of them make sense to you. So you are asked what would be the time complexity of this algorithm ending. Just think about what it is doing at each of the nodes, and if there are n nodes given, what would be the time complexity of this algorithm? And does it matter if the tree is balanced or unbalanced? So you are just given that if the value of the node will be even, then it is going to traverse the tree in one particular order. Otherwise, it will traverse the tree in another order. So just think about how much time, like how many times will it visit the each node, and that would just be your time complexity. Because on visiting each of the node, you are just deciding upon the order, and which is a constant time operation. So it just depends upon how many times you are visiting each of the nodes in the tree. Okay, any guesses, anyone? Okay, anyone else? So one way to do it is just to implement this algorithm on any binary tree, or maybe the binary tree we saw before this, or just you can just draw a random binary tree and just apply the algorithm on this and see how many steps are there. Okay, so this was a binary tree that we took as an example. What does the algorithm say? Just look at the algorithm. So if you're given a tree t as an argument, okay, tree is not nil, so it's not an empty tree, so we get into the loop. Now once we are in the loop, if t dot value is even, okay, then it will go to left node and then the right node, and then it will print its own value. But if the value of the tree is odd, then it will print its own value, then we'll go to the right and then to the left. Okay, so the first, if we take this as our exemplary tree, the first node will start with the root. Okay, the first node is 8, okay, and it's an even node. Okay, and we are given that if it's even, then we go to the left child, which is 3, then to the right child, which is 10, and then we print the value of 8. So, and we wouldn't actually be printing value of 8 now, because going to the left child, let's say 3, will again cause a recursion, and then depending on the value of this node, this is an odd node, so we'll first visit 6 and then 1, and then it will print its own value. Okay, so you have to think in terms of that. Now you're given, yeah, okay, Vaishnavi, that is the correct answer. So you have to just think about starting at the root node, okay, and you're visiting the children in one particular order. Okay, and will that order will it actually change the time complexity if your tree was balanced or unbalanced? Okay, and or would it be independent of that? Okay, if you are anyway going to visit all the nodes, then does it really matter what order did you visit them in? So you're given this tree, let's say, and you're given this traversing order, and now just guess what would be the time complexity of the algorithm given this information.
Sir, order n.
Why would it be order n?
Sir, suppose let's take BST, which has all the values which have
Okay.
odd numbers. I'm just thinking out
Yeah.
loud.
Yeah.
Now, if we have all the values that are odd, then we will continue to go right. Let us take it even. To मतलब हमारा intuition हमें left जाने के लिए बोलता है पहले. तो हमने even ले लिया सारे के सारे 2 4 6 8 10 12 ऐसे करके हैं. And then we go left. We will complete exhaust all the elements on the left. Basically जो left हमारा जो branch है पूरा उसको complete करेगा. फिर एक एक करके वापस जाएगा.
Right.
तो every node is being visited. फिर वो right में जाएगा वो तो.
How many times?
Every node will be visited. ये यहाँ पे आया. फिर दूसरी बात twice, 2 times.
Okay.
So it would be 2n basically. So order of n.
It will still be order of n. Yeah, that is the correct answer. So independent of the ordering of the visits, if it's an odd number, you're visiting right first. If it's an even number, you're visiting left children first. But irrespective of that, you're visiting every node once, okay, and you're just printing its value. So if you're given n nodes, then you would be visiting every node once only, and just the order of visit will change depending on the value of the node, if it's even or odd. But regardless of those values, you are going to visit each node once and print its value, and so the algorithm will have time complexity O n. and doesn't matter if it's balanced or unbalanced. So this tree that you see here, it's an unbalanced tree, and still you're going to visit all the nodes once, exactly once, and the time complexity will be order n. So if this example was not clear to you, if you have any doubt or anything, you ask right now. Okay, in case it's clear, we'll move on. So ON is the answer here. So the next problem. So you are given a traversal order here like before, like in the previous question. What is the traversal order? You are visiting left subtree first and then right, and then you are going to print the value of the node or the root. Okay. So with this ordering, you are given a sequence that comes out. Okay, so you started with the root, okay, then you moved left, okay, and then you moved left here, and then you moved left here, and then you printed this value. Then you move to right and exhaust all the things here, and then you print the node's value. Okay, so the order is left and then right and then its own value. Now remember, if you go left, it will basically start another recursion. So once you are left, then you are actually going to go left again, okay, because it's a recursive thing. And you are given the sequence of nodes that are printed here, okay, and from the sequence of nodes you have to construct the tree back, okay, and you are asked a question about is the left child of the root. But apart from the question, the whole thing just boils down to you're given a sequence of the output, and from that output you need to construct the tree back. Okay, so just think about how these values will come about. Okay, so where should you start with in the sequence, okay, given the traversal order, and just try to construct the tree back and take your time. I'm going to give you ample amount of time in this question because it can get a little tricky, and we'll look at the solution patiently, but it's really important that you try the question yourself. It doesn't matter if you come up with wrong tree or if you do not get it at all, like the attempt is important. Solution will anyway eventually look at. So just give it an honest attempt and see if you can actually answer the question. Okay, we have got some cases here. Let's look at the previous tree that we have. Okay, so this was the tree that we are given. Okay, and the order of traversal is so first you are visiting the left child, then the right child, and then the root. Okay, left, right, and then root. So how do we visit? So let's see the sequence that will come out of this tree. Okay, so we start with the root 8 here. All right, then basically we'll move to the left child 3. Okay, and then the left child 1. Okay, now 1 doesn't have any left or right children, so we are going to output 1 here. Okay, then we move to the right child of 3, which is 6. Okay, and then to the left child of 6, which is 4. 4 is leaf node, so we are going to just output it. So you have 1 and then 4. Okay, then we move to the right child of 6, which is 7. Okay, and now there are no more other children, so we are going to output 6 itself. Okay, and then 3 itself. Okay, and then we move to the right child of 8, so which will be 10. Then we go to 14 and then to 13, so the output will be 13 here, and then traversing back, then it will be 14, then 10, and then finally the root node 8. Okay, so how does this sequence come? Is that clear to you guys? Like, we are given an exemplar tree and given this traversing, yeah, so given this traversing order, we get this particular sequence. So is that clear to you? Because this needs to be clear if you need to construct the tree for this given sequence. So if the example and how the sequence comes for this particular binary search tree is clear, then you can attempt the next part. So just look at this sequence that is outputted and see that if you can output the sequence yourself, and if not, then you ask me now, like which part is not clear.
Sir, may I attempt?
Yeah.
It is clear from this example and from how post order traversal is being done. पहले हम लोग left subtree देख रहे हैं, फिर right subtree देख रहे हैं, and then finally they list out the value at the root.
Yeah.
So it was clear from the beginning that the root would be the last element of the array.
Good. Yeah.
So जैसे इसका भी दिख रहा है 8 हमारा जो root है वो last element है.
Yes.
उसके बाद दूसरा ऑब्जर्वेशन ये है कि the first element of the array would be the leftmost element because वो सबसे पहले प्रिंट होगा. और आप when you were explaining it, you actually gave the hint. The first line that you said was कि we will just start from left. हम लोग पहले left को exhaust करेंगे, लेकिन left को exhaust करने के लिए basically हमें उसके जो right सब trees हैं उसको करेंगे, फिर हम node पे जाएंगे. So यहाँ पे क्या हो रहा है, पहले 1 और अब 3 जो नोड रूट है, जिस सब ट्री का रूट बना रहा है वो, उसमें हमारे पास 1 हो गया. 1 से हमने स्टार्ट किया, फिर हम 6 पे गए. 6 तो हम कर नहीं सकते प्रिंट, हमने पहले 4 को प्रिंट किया, 7 को प्रिंट किया. मैं अब उसके बाद मैंने देखा कि वेयर डज 8 फिट इन दिस रूट. मैं अब एरे से वापस स्ट्रक्चर बनाने की कोशिश कर रहा हूँ. आई थिंक इट इज क्लियर दैट अगर मैं इसको इट इज अल्टीमेटली अ BST, या मैं पहले दे रखा है. तो अगर हम उसको एक ऑर्डर में कन्वर्ट मतलब उसका सॉर्ट करें उसको, तो हमारे पास आता है 1 3 4 6 7 1 3 4 6 7 8. we can वो बाकी बचे एलिमेंट्स के बारे में we don't have to think. So it is clear to me that 1 6 4 1 3 4 6 7 8 and 10. So it is clear to me that 10 would be the next right element. ठीक है, तो उसके सारे के मुझे अब now I'm sure कि मेरे को बाकी बचे एलिमेंट से कोई मतलब नहीं है. अब मैं इन पे फोकस कर सकता हूँ, बट मैं इतना सोचने की जरूरत नहीं पड़ी मुझे इस क्वेश्चन में जो आपने दिया हुआ है. उसमें क्लियरली है रूट नोड वुड बी 17. I will start with 7. I know that 25 would be the right element of 17. So I have 3 points of information. रूट हमारा 17 है, लेफ्ट मोस्ट एलिमेंट 7 है, और जो 17 का राइट एलिमेंट है वो है 25. ठीक है. अब मुझे पता है कि
there's little error in that, like but go ahead, like you're doing very well, like there are just little errors here and there.
Okay, हाँ please बताइएगा.
So
So I start with 7 and then I have to observe. मुझे थोड़ा सोचना पड़ेगा कि क्या उसका राइट सब ट्री हो सकता है, मतलब जो उसका ट्री है, सपोज वो 12 है, then I have to once again go to its root. क्या 25 इसका रूट होगा? नहीं. क्यों? बिकॉज वो 17 से बड़ा है, मुझे पहले ही पता है.
exactly,
और
yeah,
वो 17 से छोटा होना चाहिए अगर वो 17
yeah,
के लेफ्ट में है.
yes, yes,
तो मैं वहीं
yes,
पे
yes.
सॉर्ट कर देता हूँ और मुझे पता चल जाता है कि 7 और 12 जो है वो बेसिकली एक क्या बोलते हैं, मतलब जो 12 है, 12 का चाइल्ड 7 है, लेफ्ट चाइल्ड, और उसका राइट चाइल्ड कोई नहीं है. तो 7, 12 और फिर 17 आ जाता है हमारे पास,
Exactly. Yeah.
ऐसे करके.
Yeah. That is the correct solution, and it is a clever solution. You don't have to look at the whole tree for this, but you can also construct the tree honestly from this and then look at it. But anyway you'll get the full marks for this thing because you just looked at the left tree instead of looking at the whole thing. Okay, we are going to look at the solution step by step now, and let's see how to construct the complete tree from the given sequence. Okay, so what we are given, as Rahul pointed out, we have to look at the last element 17 because this will be our root node. Okay, and this is the first step in constructing the tree. Like, grab the last element, and because you know that the traversal pattern is left and then right and then the root, so you know that the root node will have to come at the very end. Okay, so from this information we start making our tree. Okay, so we put 17 as a root node. Okay, now this is a binary search tree, so all the elements that are smaller than 17 are going to come on the left of 17, all the elements bigger than 17 to the right. All right, so we take the next value, which is 42. Okay, so where do you think 42 is going to come?
Right side.
Yeah, so 42 will be the right child of 17. And does it make sense to you why it is 42 as the right child and why it is not, let's say, a grandchild of 17? Like, why is it an immediate child of 17? So remember, what is the traversal order? Left, right, and then root. So what do you think? Why 42 should be the child? Or should it
Because
be?
right child,
Because right? Come again?
because right child is printed before the root node.
Yeah, yeah. So the traversal order is left and then right and then the root. So when we would be completing the right subtree, we'll print the root here of the right subtree, which is the right child, and then we'll put basically the right the root of the element. So if you'll go back to our example tree, so here if you look at 10, so 10 is basically the right child of 8. Okay, and it came just before the root. So we know now two things, that the root comes at the last and the right child comes second last. Okay, so we have these two things now. So now we look at the next number, 55. Now tell me, where will 55 go?
Right side of the 42.
Okay, why not left side?
Because 55 is greater than 42.
Yeah, correct. So it will come here as 55. Okay, now moving on, 89. Tell me where it will go.
Right child of 55.
Correct. Then 47. Now be careful. It can be at multiple places.
Left child of 55.
Are you sure?
Yes.
Yeah. It will be left child of 47. Will be the left child of 55. Basically, so how we were traversing is, now think about it, like when we are writing the algorithm. So we are going to the right subtree of 17, 42. So we do not print these values. We are now just visiting these nodes. We visit 42, visit 55, then visit 47 and print it. Okay. So 47 comes here in the sequence. Then we visit 89, print it. 89 comes. Then we print 55. Then we print 42 and then 17. So does the sequence make sense to you? And why 47 should be the left child of 55? If anyone of you have any doubt, like, just ask right now. It's important to get the traversal orders in your head and to apply them correctly for binary search trees. Okay, moving on. Then 25, where will 25 come?
Left child of 47.
Left child of 47.
Yes, sir.
Okay,
42.
it is left child of 42 because you cannot have values smaller basically than 42 in the right tree. You get it? It's a binary search tree. So
Okay, sir.
all the values which are less than the root has to come in the left child or the left subtree. So you have 25 and it cannot actually come below 47, so it will be actually a left child for the parent node of it. Okay, is this point clear? Like, always remember the property of a binary search tree. Like, numbers less than the root goes to the left, numbers more than the root goes to the right. Okay, and this will save you from any inconsistencies. Okay, then the next number 12, where will that come?
Left child of 17.
It is left child of 17, and then 7 as the last child of 12. Okay, look at this tree carefully and look at the sequence that is given. See if this sequence actually comes from this tree, and if you have any doubt about how we backtrace from the sequence to this. So if someone has a WhatsApp link to the group, they can ping it. I think Ram needs it. Otherwise, Ram, you can find it again on the discussion forum of the course. So there are links available there. You can also check your Gmail. You might find the link there. Okay, in case this question is clear to everyone, we'll move on. So here basically you are asked what is the left child of the root node 17. Of the root node, they are not given 17 as the root node. You have to figure that out. And 17 is the root node and its left child is 12. So 12 is the answer here. Okay, fine. We'll move on to the next problem. So this problem is related to Huffman coding. Okay, and you are given, so just attempt this question with the knowledge that you have about the Huffman code. Okay, and you are given 4 symbols here, A, B, C, D. You are given the probability of occurrences of this symbol. You are given this inequality basically. You are given FA is greater than FB is greater than FC is greater than FD. So A, B, C, D are the probability of occurrence is in that descending order. Okay, and you are asked about if how many bits will be assigned to each of this A, B, C, D. So A, B, C, D are basically, let's say, the alphabets that you want to communicate, and you are going to communicate it with, let's say, zeros and ones. Okay, so Huffman code basically converts these A, B, C, D into a binary code, 1001, whatever you can get. And what code it will use depends on how frequently these symbols are occurring, A, B, C and D. Okay, so if A is occurring a lot of times, okay, then you would want to basically put just let's say 1 bit assigned to it. So A is just, let's say, 1. Okay, so basically if A is occurring a lot of times, then you have to send A a lot of times, and you want to send a lower bit number than a higher bit number. So the symbols that are occurring a lot, you want to use less number of bits for those symbols. The symbols that do not occur so much, you don't mind encoding them with a bigger number. Let's say if D doesn't occur too much here, you might want to encode it with like 1110 or something, like 3 bits for it, because these 3 bits are not going to be sent so many times. Okay, so all in all, you're given a probability relation here, and you're asked about little more information if you're given about this probability relation, and particular information is like FC and FD, FC plus FD, and their values compared with FA and FB. Okay, and how this comparison, whether these values are greater or smaller, how will it change the number of bits that you are using to encode the symbols. Okay, so if you have gone through the content related to Huffman code, then it's a pretty straightforward problem, and I just want you to attempt it once and guess your answers, then we'll look at the theory part. Anyone wants to take a guess? Okay, I'll just tell you the theory part, so then you can attempt it more fairly, I guess. Okay, so let's say we are so these are from your lecture slides, so you can revisit this example if it's not clear to you. So we are given 5 symbols, okay, A, B, C, D and E, and you need to encode them. So encoding them is just basically giving them a representation in binary. So let's say you want to represent them with 0 and 1s, okay, so you want to, let's say, represent A with 1 0 and B with 1 1 0 and so on. So every symbol will have a binary representation. Okay, so how do we come up with this binary representation? So you are given this probability of occurrences of the symbol. So A has 0.32, B has 0.25, C 0.2, 0.18 and then E has 0.05. Okay, so what is the Huffman algorithm? So what will Huffman algorithm do is it will keep clubbing your least probable symbols. So here the least probable symbols are D and E. Okay, so as the first step of the Huffman algorithm, you club these two symbols. So once you have clubbed them, they become D, E. Okay, and their probability of occurrence is just added. So you have 0.18 plus 0.05 gives you 0.23. Okay, and your rest of the symbols are same. Okay, and now you are going to again, so and you keep basically repeating this clubbing process. So what are the next symbols that you are going to club? It will be D, E and C, because these are the two least probable symbols right now. So A and B are both occurring more frequently than C and D, E combined. Okay, so now we are going to club C, D and E. Okay, so you have A, B and C, D and E. Okay, now C, D, E combined probability becomes 0.43. Okay, and this probability has become more than A and B. So now your least occurring symbols are A and B. Okay, So what will be the next step? You're going to combine these two symbols, A and B. Okay, so you have AB now, which occurs with 0.57, and CDE. Now there are no more symbols left for clubbing, so it's just ABCD, the whole thing. Okay, so now we convert this clubbing into a tree structure, and how will that look like? So for the last value AB and CDE, so we just treat them as two nodes. Okay, AB and CDE. So the tree would look something like this. So there's a root node here. It has left child as AB and right child as CDE. Okay, like AB and CDE. Okay, and now we basically keep going a step up to get the original symbol A, B, C, D and E. Okay, right now the symbols are in clubbed form, so we need to unclub them. Okay, and how are we going to unclub them? So the next symbol that we are going to unclub is AB. Okay, because that is the step previous to it. So we clubbed AB, so now we are just back tracing it, so we are going one step backward each time. So we unclub AB and it becomes something like this. So we have again root node and then the node, and this AB club node has split into two, A, B and CDE. Okay, now we go another step back, and what will we unclub now? We'll unclub CDE basically, and CDE unclubs into C and DE. Okay, so the next step becomes this. So we have unclubbed CDE and we got C and the combined symbol DE. Okay, and as the final step we are going to do AB. We are basically just going to unclub DE now, and once we unclub it we get this tree ABCDE. Okay, just look at the slide carefully, look at the numbers that we started with and look at the tree that we got from it. Okay, if you have any doubts in any of these steps, you ask me. Okay, so far we were given a set of 5 symbols A, B, C, D, E. We are given the probability of their occurrences, alright, and what we are asked is to convert these symbols into a binary representation. What we have done so far is constructed a tree. Okay, and now how does this tree help us to get those binary numbers? So what we do is, once we have got this final tree, okay, with all the symbols unclubbed, individual leaf nodes they are now A, B, C, D, E. So we basically assign all the left branches the symbol 0, let's say, and all the right branch we assign 1. Okay, so what would be the encoding of A? So starting from the root node, you go to left, okay, you reach the left child, and then you again go to left and then you reach A. Okay, so the symbol of A is like it's left and then left, so it is 0 and then 0. Okay, you get it? So A becomes 0, 0. And similarly now B, to reach B you have to take one left and then right, so it is 0 and 1. Alright, so A is 0, 0, B is 0, 1. What is C? C will be 1 and then 0, and D will be 1, 1, 0, and E will be 1, 1, 1. Okay, you got it? So I'll just write down the encoding. So A becomes 0, 0, B becomes 0, 1, okay, C becomes 1, 0, and D becomes 1, 1, 0, and E becomes 1, 1, 1. Okay, so the specialty of Huffman code is, so if you are given any basically any binary sequence, then you can decode the binary sequence without any conflict. Okay, like if let's say you're given a binary sequence which is something like okay, so it can be something like, so you are given this as a binary sequence, so it's 1 0 0 0 0 1. Okay, so what would be this what will be this word? Okay, so we are given the table we are given. So you should all look in the chat box if you don't know. So in the chat box I have given you the symbols of each, the binary representation of each symbol, and you're given a final binary word and you need to decode this word. So can anyone decode the word? What would be the word be for this given binary representation? And can you decode this word without conflict, or can there be multiple possibilities? Anyone? I hope this was clear, that how these binary representation came about from the tree. Yeah, the word is cab. So you start with looking at 1. Okay, now you see that there are multiple symbols that start with 1. Okay, it can be C, D or E, but the next digit following 1 is just 0. Okay, and D and E doesn't have 1 0. Okay, so 1 0 is only with C, so 1 0 can only be C, so you stop your search here. Then the next number is 0. Now 0 occurs in A or B, okay, but the 0 is followed by another 0, so you're sure that it was going to be A. Okay, so you stop your search. And finally you have 0 again, it can be A and B, but it is 0 and 1, so it can only be B. So all in all, the whole crux of Huffman algorithm is that depending on the probability, it gives you symbols or binary representation, and these binary representation are efficient, as in the symbols that are occurring with more probability will be given a shorter binary representation. Okay, and these binary representation, if you're going to use, you can use them without any conflict. So it doesn't matter what basically what words you make out of this binary representation, there will never be a conflict, as in this sequence can represent this word or this word. It will always represent a unique word. Okay, and you can try to figure out why is that. So the whole secret lies in this tree, how we are constructing the tree, and how there will never be a redundancy, basically no conflict in the representation. Okay, now given this much of information, I want you to basically try this question again. Okay, so you, in the options, basically you're given 2 condition here. Okay, so you're actually given 3 condition. One on like 2 of the conditions are on FB, if FB is less than FC plus FD, or FB is greater than FC plus FD, and there is one condition given on FA, if FA is less than FC plus FD, or, and you're given how will your number of bits representing these symbols will change. So just attempt it. I'll give you a minute or 2 to think about it. Like maybe you have gotten the answer with the information. So all you have to see is how will the trees get split. Okay, if the trees are splitting equally, like so, if you have 4 leaf nodes, you have only 4 symbols here now. So root, and then A, so left child, then AB, and root, right child, and CD. So then you get equal number of bits. Okay, it will be like 0 0 0 1 1 0 and 1 1. Okay, you'll get unequal number of bits if AB and CD are not clubbed, if basically BCD is clubbed and A is left out. So just think about when will this BCD be clubbed. Okay, so from the algorithm, the first thing we know off the bat is the last 2 symbols will be clubbed. There is no doubt about it. So we know C and D are going to be clubbed. Okay, now the whole question lie, once your CD is clubbed, then will your AB be clubbed or BCD will be clubbed. So these are the 2 cases, and just think about when will these 2 cases occur. Okay, when will how will you decide to club B with A or club it with CD? Like that is the whole crux of this question. Anyone else want to guess? Sashi, okay, let's discuss it in the end. Yeah, we can surely discuss it. Okay, so coming back to this question, so you have two cases that are given here, right? Or let's say three cases. So you have FA less than FC plus FD. What happens in this case? Okay, so basically if your FA is less than FC plus FD, then you know that A and B are going to be clubbed together. Okay, so we had this condition right now. So let's say we are given this 0.32, 0.25 and 0.43. Now in the next state what happens is point A and B are clubbed together. Why? Because the probability of A is less than the combined probability of CDE. Okay, in the question we are given 4 symbols, so let's treat that CDE as just comprising of 2 symbols, but the essential part is whether B gets clubbed with A or if it's clubbed with CD. It depends on the probability of A and the combined probability of CD. It doesn't depend on the probability of B, because we are anyway given that FB is less than FA. Okay, so the case that is going to decide the clubbing is just this: if FA is less than FC plus FD or not. If it is less than FC plus FD, you get this case. If it is greater than FC plus FD, you get this case. Okay, in the lower case that you are shown here, so the symbols will be encoded with varying bits. A will just be 0, B will be 1 0, C will be 1 1 0, and D will be 1 1 1 1 1 1 1. Okay, and if your FA is less than FC plus FD, then you basically get an equal number of bits. So that's why your correct answer becomes C. If FA is less than FC plus FD, then you get equal number of bits, otherwise varying number of bits. The other two option which were related to FB, they are meant to like just throw you off, because Hoffman coding actually doesn't depend on FB, it depends on FA, because you're already given the starting relation saying that FB is already less than FA. So all it boils down to if FA will be less than the clubbed probability. Okay, I hope this is clear. Like if it is not, just go over Huffman coding once more, try to encode some values yourself and see how the algorithm flows basically, and then you can come back to the question and check it. Okay, Sashi, what is your question exactly regarding space complexity?
So I just want to know, I mean, if you can show an example that how we calculate this on.
So you mean space complexity as in the memory that an algorithm will take, right?
Yeah, I mean, in Gate sometimes they ask questions.
Yeah. Okay, so see, when you are talking about space complexity, so what you have to, let's say I give you an array, okay, and which has n elements in it, okay, so and I tell you to find the maximum element of the array. Okay, so you're given an array of n elements, and you have to look for maximum out of this thing. So what would be your best algorithm to do it? Like think about what is an efficient algorithm to look for the maximum.
Bubble sort?
Okay, do you need to sort them? You just need to find the largest element. You do not need to order all of them. So any sorting algorithm, the time complexity will be O n log n, and better algorithm is just to maintain one variable and this variable basically stores the maximum value that you have seen so far. Okay, and you're given an array element, and you're just going towards each of the element. Okay, and you are basically storing the maximum value you have visited so far, and you are going from 0 to n or n minus 1. Okay, looking at each of the value, and you only need one variable then in this case, which will store the maximum value. If it finds a value greater than its own value, it stores that value. Okay, and this you keep doing till the end. So you are looking at each of the elements only once, so your time complexity will be on. Okay, and now what you have to think about is what will be your space complexity here. So because you only have one element here, okay, and which is going towards all of the array, like the whole array that you saved, okay, and you do not need any more variable than that. Okay.
I mean, if the array is sorted, do we really need to search it? I mean,
yeah, I'll come back to that example too. So if you are sorting the array, let's say, okay, and you are let's say doing okay, let's say you are doing, what can you apply, like if you are doing quick sort, then also your space complexity will be same. But if you are doing so in most of the cases the space complexity remains O1 because you do not need to create any more memory. But let's say if you have a sorting algorithm that copies your original array into another array, okay,
like merge sort.
Yeah, exactly, like merge sort. So in that you have to, in addition to your original array, whatever memory it was taking, let's say you had a big array originally, okay, and it was taking 1 GB of memory, and you are applying merge sort in it, okay, and you are maintaining another array in which you are putting back the already sorted components of your array. So you had original 1 GB of space which this array was taking, and then you need another 1 GB of free space in which you will keep basically putting your elements in order. Okay, so you need like 1 GB plus 1 GB. Okay, so generally you will say that merge sort then has a space complexity of on, okay, because you need to assign it as much space as you had originally. So you had n elements originally, and you are assigning that much order again, so space complexity becomes on. But with something like, I think, selection sort or any other of these kind of algorithm, your complexity will just be O1, because you can just use the same space that you had. Like if you have already loaded an array into your RAM, okay, so once it's loaded in the RAM, and you do not need to make any more copies of that array, okay, you can use that same RAM and you can just reposition your elements, okay, without needing further memory. Then you will just say that the complexity is O1, space complexity, like it doesn't require any further memory. Okay, so that's how you just look at the space complexity. Just look at all the variables in your algorithm and look at how much space they are going to take. Are they going to be taking space that was equal to original array? Then it will be of the order n. If they are, maybe you have to take, like from an array you are now making an n into n matrix, okay, then it will be O n square, okay, and so forth. So in terms of
if there is no change in the use of memory, then we can have big O1.
Yeah, exactly.
And it's a constant.
Yeah, it will be just a constant. It's just like if you're like in the example, if you're just finding a maximum, then you just need to maintain one variable, okay, and this variable will have a constant size. So if it's an integer array, then it will take let's say 4 byte of space. So this 4 byte is constant, and it is irrespective of how long your original array is. So it doesn't matter if it's 1 GB, 2 GB, you just need to always assign just a 4 byte variable, and this 4 byte variable will contain your maximum value it has seen so far while it is traversing the whole array, and you do not need to assign any more values, any more memory. So it will be like order 1. Okay.
Okay. Thank you.
Okay, so this was all the questions that we have for this week, and just go through the content once more. If you have any doubts, so please don't hesitate to post it on the WhatsApp or discussion forum, and I'll see you guys next week, same time.